Welcome to today's session. We'll be diving into problem number 1073, titled Adding Two Negabinary Numbers. This is an interesting problem that explores the concept of Negabinary representation, which is a lesser-known but fascinating number system. Get ready to unravel the logic and solve this step by step. In this problem, we are working with numbers represented in the Negabinary system, which uses base -2 instead of the usual positive base systems like base 10 or base 2. You are given two arrays, ARR1 and ARR2, where each array represents a number in this Negabinary format. The most significant digit appears first, and there are no leading zeros unless the number itself is 0. The task is to return the sum of these two numbers, also in Negabinary representation, as an array. For example, if ARR1 is 1, 1, 1, 1, 0, and ARR2 is 1, 0, 1, we need to compute their sum in this base -2 system and return the result as an array. The output for the first example is 1, 0, 0, 0, 0. To understand this, we first calculate the decimal values of ARR1 and ARR2 based on their Negabinary representations. For ARR1 equals 1, 1, 1, 1, 0, the value is 4, derived from the formula 1 times -2, 4, plus 1 times -2, 3, plus 1 times -2, 2, plus 1 times -2, 1, and finally 0 times -2, 0. Similarly, for ARR2 equals 1, 0, 1, the value is -2. Adding these, we get 4 plus -2, which equals 2. Finally, converting 2 back into Negabinary gives 1, 0, 0, 0, 0. Another simple example is when both arrays are 0, resulting in a sum of 0, since both numbers represent 0. In the third example, ARR1 equals 1 and ARR2 equals 1. The decimal value of ARR1 is 1, and the decimal value of ARR2 is also 1. Adding these gives us a sum of 1 plus 1, which equals 2. Now, the Negabinary representation of 2 is 1, 1, 0, which is the output for this example. This demonstrates how Negabinary naturally handles addition, even though the base is negative. The key is to carefully interpret the powers of -2 for each digit and apply the rules of Negabinary addition when constructing the result. There are several important constraints and edge cases to consider for this problem. First, the lengths of ARR1 and ARR2 can range from 1 to 1000, so your solution must be efficient in both time and space. Each digit in the arrays is either 0 or 1, and there are no leading zeros unless the number is 0. For edge cases, if one array is 0, the result is simply the other array. Additionally, if the computed sum has leading zeros, they should be removed from the result. The Negabinary system also handles negative sums automatically, so you won't need special logic for subtraction-like cases. Finally, since the input size can be large, it's crucial to handle the computations efficiently without unnecessary overhead. To tackle the problem of adding two Negabinary numbers, we need to choose the right approach. A brute force solution might be the first idea that comes to mind. This involves converting the input arrays, which represent numbers in base -2, into their decimal equivalents. Once in decimal, we can perform a standard base 10 addition and then convert the result back to base -2. While this method is straightforward, it's not very efficient. The conversion processes, from base -2 to decimal and then back again, can become computationally expensive, especially when dealing with long input arrays. Additionally, these conversion steps might result in handling large intermediate values, which further adds to the inefficiency. From a complexity standpoint, it involves n superscript 2 time because the repeated division and modulo operations for base conversions grow with the input size. The space requirement is n, as we need to store the intermediate decimal representation. These drawbacks make the brute force approach unsuitable for larger inputs, prompting us to explore a more optimized strategy. One such efficient solution is the digit-by-digit simulation, which directly operates in base -2, eliminating the need for conversions entirely. To implement a more efficient approach, it's essential to understand the nuances of base -2 arithmetic. In base -2, although each digit is either 0 or 1, the behavior of carries is quite different due to the negative base. A key observation here is that when a carry occurs, it propagates not just to the next digit, but to the next two higher places. This creates a balancing effect that must be carefully managed during the addition process. By processing the digits from right to left, starting with the least significant digit, we can build the result incrementally. The process begins with 2 pointers positioned at the end of the input arrays. At each step, we add the corresponding digits from both arrays, along with any carry from the previous step. The result is then normalized to ensure that each digit remains within the valid set of 0, 1, and the carry is updated accordingly. This process continues until all digits have been processed, and any remaining carry is also accounted for. Lastly, we remove any leading zeros from the resulting array to ensure the output is in its proper minimal form. This approach is significantly more efficient, with a time complexity of O, max, n, m, where n and m are the lengths of the input arrays, since we process each digit only once. The space complexity is also O, max, n, m, as the result array grows proportionally to the size of the inputs. The optimized approach offers several distinct advantages. By working directly in base-2, it eliminates the need for unnecessary conversions, which not only saves time but also avoids the overhead of handling large intermediate values. This makes the method particularly well suited for handling large inputs efficiently. The process is clear and systematic, breaking the problem down into manageable steps that align closely with how addition is performed in other bases. This strategy was chosen for its balance of efficiency and mathematical elegance. Unlike the brute force method, which relies on intermediate representations, the optimized approach directly addresses the problem at its core. One of the key realizations that makes this method work is understanding how carries propagate differently in base-2. By normalizing the result at each step, we can simplify the process and ensure correctness without extra intermediate steps. While this approach is slightly more complex to implement compared to brute force, its advantages in efficiency and scalability make it the superior choice, especially in competitive programming scenarios where performance is critical. In summary, the chosen strategy strikes an ideal balance between clarity, efficiency, and correctness. By directly manipulating the Negabinary numbers without relying on conversions, it provides a solution that is not only computationally efficient but also elegant in its design. This makes it the perfect approach for solving the problem of adding 2 Negabinary numbers. The optimized strategy leverages critical insights about base-2 arithmetic, such as the unique behavior of carries, to deliver a robust and scalable solution. This combination of systematic processing and mathematical understanding ensures that the method is both effective and intuitive, addressing the problem requirements comprehensively. To solve the problem of adding 2 numbers represented in Negabinary, we need to approach the task step by step. The numbers are provided as arrays, where each digit represents a value in base-2 and the least significant digit is at the end of the array. The goal is to compute their sum and return it as an array in the same Negabinary format. The first step is to reverse both input arrays, ARR1 and ARR2. Since the least significant digit is at the end, reversing the arrays allows us to process the numbers from the least significant digit to the most significant digit. This is similar to how we handle addition in standard binary or decimal systems. It simplifies the process of aligning the digits and managing carries. To prepare for the addition, we also initialize a result array to store the digits of the sum in reverse order, and a carry variable, starting at 0. This carry will help us handle situations where the sum of 2 digits exceeds the range of valid Negabinary values or becomes negative, which is unique to this base system. Now, we perform the core operation, digit-by-digit addition. To do this, we iterate through the longer of the 2 arrays, padding the shorter one with zeros as needed. For each digit position, we add the corresponding digits of ARR1 and ARR2, along with the current carry. The result of this addition determines the digit to append to the result array and the new value of carry, based on Negabinary rules. If the sum is 0 or 1, no carry is needed, and we append the sum directly to result. If the sum is 2, we append 0 to result and set carry to -1. Similarly, if the sum is -1, we append 1 to result and set carry to 1. These rules ensure that the resulting number remains valid in the Negabinary system. Once all the digits have been processed, we check if there is any remaining non-zero carry. If so, we continue processing the carry by appending the appropriate digits to result and updating the carry value until it becomes 0. This ensures that the final result accounts for all the values correctly. To better understand this algorithm, let's consider some key insights. First, in Negabinary, each digit position corresponds to powers of -2, such as 1, -2, 4, -8, and so on. This means that carries can propagate differently compared to other bases. For example, a sum of 2 in Negabinary requires a carry of -1, and a sum of -1 requires a carry of 1. These properties make carry handling in Negabinary unique and require careful adjustment. Additionally, we must handle edge cases, such as when one input array is much longer than the other, or when the final carry introduces extra digits that extend the length of the result. Another edge case involves removing leading zeros to ensure the result is in its minimal representation. If the result becomes empty after this step, we return 0. From a data structure perspective, arrays are ideal for this problem. They allow direct indexing, easy reversal, and efficient manipulation of digits. In terms of complexity, the time complexity is O, max, n, m, where n and m are the lengths of the input arrays, as we iterate through all digits and handle the carry. The space complexity is also O, max, n, m, as the result array will be at most one digit longer than the longer input array. Let's walk through a specific example to see the algorithm in action. Consider the inputs ARR1 equals 11110 and ARR2 equals 101, which represent the numbers -6 and 5 in decimal, respectively. First, we reverse the arrays to get ARR1 equals 01111 and ARR2 equals 101. We then initialize result equals and carry equals 0. We start adding the digits position by position. At position 0, the sum is 0 plus 1 plus 0 is equal to 1. We append 1 to result and keep the carry as 0. At position 1, the sum is 1 plus 0 is equal to 1. Again, we append 1 and the carry remains 0. At position 2, the sum is 1 plus 0 is equal to 2. According to Negabinary rules, we append 0 and set carry to -1. At position 3, the sum is 1 plus 0 minus 1 is equal to 0. We append 0 and reset the carry to 0. Finally, at position 4, the sum is 1 plus 0 is equal to 1. We append 1 and the carry remains 0. After processing all digits, we reverse the result array to restore the correct order, yielding 10011. Removing any leading zeros leaves the final result unchanged. This corresponds to -1 in decimal, which is the correct sum of the input numbers in Negabinary. Therefore, the output is 10011. Here, we start by defining a class called solution and implementing the function addNegabinary within it. This function takes two arrays, ARR1 and ARR2, which represent numbers in base -2. To simplify the addition process, the arrays are reversed so we can begin adding from the least significant digit. Next, we initialize a carry variable to handle overflow during addition and create an empty list called result to store the digits of the final sum. The function then iterates through the maximum length of the two input arrays. For each position, we extract the current digit from both arrays, defaulting to 0 if the index is out of bounds. These digits, along with the current carry, are added together to compute the total. The least significant bit of this total, obtained using modulo 2, is appended to the result. To prepare for the next iteration, we calculate the carry for base -2 by dividing the total by 2 and negating it. This ensures that the next step accounts for the rules of Negabinary arithmetic. Now, once the main loop has processed all the digits, there might still be a remaining carry. To handle this, we continue appending the least significant bit of the carry to the result and updating the carry by dividing it by 2 and negating it, until the carry becomes 0. After the addition is complete, we remove any leading zeros from the result to ensure the output is in its simplest form. This is done by repeatedly removing the last element of the list if it's 0, as long as there's more than one digit left. Finally, we reverse the result list to restore the correct order, transforming it back from the reverse state we used for computation. The function then returns this list, which represents the sum of the two input numbers in base -2. Here, we start implementing the solution in Java by defining the class and the method addNegabinary. First, we reverse the input arrays ARR1 and ARR2 to process the digits starting from the least significant position, which simplifies the addition logic. We initialize a list called result to collect the digits of the final sum, and a variable carry to handle any overflow during addition. We also set up two pointers, I and j, to iterate through the arrays from their last indices. In the while loop, we process the digits of both arrays and the carry until all of them are accounted for. Inside the loop, we extract the current digits from ARR1 and ARR2 using the pointers. If a pointer goes out of bounds, we treat the corresponding digit as 0. The total is calculated by adding the two digits and the carry. We then append the remainder of total divided by 2 to the result list, which gives us the current digit in base -2. The carry is updated using the formula -total1, which adjusts for the negative base of the number system. After processing all the digits and the carry, we handle any leading zeros in the result list. This is done by repeatedly removing zeros from the end of the list until only one or more meaningful digits remain. Once the list is cleaned up, we convert it back into an array, reversing the order since the digits were appended from least to most significant. This is achieved by iterating through the list in reverse and storing the values in the result array. Finally, the result array is returned, which represents the sum of the two input numbers in the Negabinary format. To solve the problem of adding two numbers in Negabinary, let's start with an example. We are given two input arrays, ARR1 equals 11110 and ARR2 equals 101. Since Negabinary addition works from the least significant bit upwards, the first step is to reverse both arrays. This makes ARR1 equals 01111 and ARR2 equals 101, allowing us to process them from the rightmost bit to the leftmost. Next, we initialize two variables, carry, which starts at 0, and an empty array called result, which will store the digits of our final answer as we calculate them. With this setup, we are ready to begin adding the digits of the two arrays step by step. Now we begin iterating through the digits of the reversed arrays. For the first step, we add the digits at index 0, digit 1 equals 0 from ARR1, digit 2 equals 1 from ARR2, and carry equals 0. Their sum is total equals 0 plus 1 plus 0 equals 1. The remainder of total when divided by 2, which is total %2 equals 1, is appended to result, so result equals 1. The carry is updated to the negated integer division of total by 2, which is carry equals total / 2 equals 0. In the second step, at index 1, digit 1 equals 1, digit 2 equals 0, and carry equals 0. Their sum is total equals 1 plus 0 equals 1, so we append 1 to result, making it 1, 1, and the carry remains 0. At index 2, digit 1 equals 1, digit 2 equals 1, and carry equals 0. This gives total equals 1 plus 0 equals 2. We append total %2 equals 0 to result, resulting in 1, 1, 0, and update the carry to -1. At index 3, digit 1 equals 1, digit 2 equals 0, and carry equals -1. The total becomes total equals 1 plus 0, 1 equals 0. Appending 0 gives result equals 1, 1, 0, 0. Continuing with the iteration, at index 4, digit 1 equals 1 from ARR1, digit 2 is out of bounds in ARR2 so it defaults to 0, and carry equals 0. The total is total equals 1 plus 0 equals 1. Appending 1 gives result equals 1, 1, 0, 0, 1, and the carry remains 0. After processing all digits, we check if any carry is left. In this case, there is none, so we move to the next step. The result currently has no leading zeros to be removed. Finally, we reverse the result array to restore the correct order, resulting in 1, 0, 0, 1, 1. This is the final output for this example. Let's work through a second example to reinforce the process. The input arrays are ARR1 equals 100 and ARR2 equals 111. Reversing them gives ARR1 equals 001 and ARR2 equals 111. We initialize carry as 0 and an empty result array. Now, we are ready to add the digits step by step. Starting the iteration, at index 0, digit 1 equals 0 from ARR1, digit 2 equals 1 from ARR2, and carry equals 0. The total is total equals 0 plus 1 plus 0 equals 1, so we append 1 to result, making it 1. The carry remains 0. At index 1, digit 1 equals 0, digit 2 equals 1, and carry equals 0. The total is again total equals 0 plus 1 plus 0 equals 1. Appending 1 gives result equals 1, 1, and the carry remains 0. At index 2, digit 1 equals 1, digit 2 equals 1, and carry equals 0. The total is total equals 1 plus 0 equals 2. Appending total %2 equals 0 gives result equals 1, 1, 0, and the carry is updated to -1. After processing all array indices, we handle the remaining carry. The carry is -1, so we append carry %2 equals 1 to result, making it 1, 1, 0, 1. The carry is then updated to carry equals carry //2 equals 1. Now, with carry equals 1, we append carry %2 equals 1 to result, resulting in 1, 1, 0, 1, 1. The carry becomes 0, so we proceed to the next steps. There are no leading zeros to remove, and reversing the result gives 1, 1, 0, 1, 1. This is the final output for this example. Let's now look at a simpler case, adding ARR1 equals 0 and ARR2 equals 0. Reversing both arrays keeps them the same, ARR1 equals 0 and ARR2 equals 0. We initialize carry as 0 and an empty result array. In the first and only step of iteration, at index 0, digit 1 equals 0, digit 2 equals 0, and carry equals 0. The total is total equals 0 plus 0 equals 0. Appending total %2 equals 0 gives result equals 0, and the carry remains 0. After processing the arrays, we check for any remaining carry. In this case, no carry remains, so we move on to removing leading zeros. The result contains only a single 0, so it remains unchanged. Finally, reversing the result gives 0. This is the output for this case, and it demonstrates how the algorithm handles the simplest inputs efficiently. In this problem, the time complexity of the add Negabinary function can be broken into several steps. First, we start with reversing the input arrays ARR1 and ARR2. Reversing an array of length n takes n time. Since the two arrays can have different lengths, we define n as the maximum of their lengths, so reversing both arrays costs n. Next, we iterate through the digits of the arrays. This loop runs up to n times, where each iteration involves constant time operations such as adding digits, computing modulo, updating the carry, and appending to the result. Thus, iterating through the digits also has a cost of n. Now, after processing all the digits, we may still have a carry left that needs to be resolved. This is handled in the while carry loop. The number of iterations here depends on how large the carry is, but each iteration reduces the carry by a factor of 2. This means the loop runs at most log n times, as the carry is essentially being divided in binary. Then, we remove leading zeros from the result array. This involves iterating over the array from the end until we encounter a non-zero digit. In the worst case, if all digits are zeros, this operation costs n. Finally, we reverse the result array to restore the correct order, which also takes n time. When we combine all these steps, the total time complexity becomes n for reversing inputs, n for processing digits, log n for handling the carry, n for removing leading zeros, and n for reversing the result. Simplifying this, the overall time complexity is n, where n is the maximum length of the two input arrays. Next, let's examine the space complexity of the add Negabinary function. Additional memory usage comes from three main sources. First, reversing the input arrays creates copies of ARR1 and ARR2, which requires n space. Second, the result array stores the sum of the two input arrays in base -2. In the worst case, the result can have up to n plus log n digits due to carry propagation, meaning the space needed for the result is n. Lastly, the temporary variables used in the algorithm, such as carry, digit 1, digit 2, and total, require constant space, or 1. By combining all the contributions to space usage, we get n for the reversed arrays, n for the result array, and 1 for the temporary variables. Adding these together, the total space complexity simplifies to n. Comparing this to a brute force or naive approach, we find clear advantages. In a naive method, the input arrays would first be converted to integers in base -2, and then the result would be converted back to base -2. These conversions involve iterating through the arrays to compute the integer value, which takes n time, and repeatedly dividing the integer to convert back, which takes log k time, where k is the magnitude of the resulting integer. This approach is computationally expensive and also requires log k space to store intermediate integer values. The optimized approach provided here avoids these expensive conversions and directly performs the addition in base -2. This makes the algorithm more efficient, reducing both time and space complexity to n. When analyzing the best, average, and worst cases, we find the complexity remains n across all scenarios. In the best case, the carry resolves quickly, and the result array is similar in length to the inputs. For the average case, the carry adds a small overhead of log n, but the dominant term remains n. Even in the worst case, where the carry propagates for log n iterations, the overall complexity is still n, because array processing steps dominate. To solidify this, we can mathematically prove the big O complexity. The linear time complexity arises because the algorithm processes each digit of the input arrays in n, and performs constant time operations during each iteration. While carry resolution adds up to log n additional steps, this is negligible in comparison to the dominant n term. Similarly, the space complexity scales linearly because we store reversed copies of the input arrays and the result array, both of which are proportional to the input size. Thus, the overall space complexity is n, confirming that the algorithm is both time and space efficient. Let's start by addressing some of the most common mistakes when working with Negabinary numbers. First, there's the misunderstanding of Negabinary representation itself. Unlike standard binary, which is base 2, Negabinary operates in base -2, meaning the powers alternate between positive and negative values, such as 1, -2, 4, -8, and so on. For example, the Negabinary number 110 doesn't equal 6 as it would in binary, instead, it represents -2. Misinterpreting this can lead to completely incorrect results. Next, we have the issue of directly converting large Negabinary numbers to decimal. While this might seem straightforward, it can lead to computational limits or even crashes due to precision errors, especially when working with very large inputs. Another critical mistake is improper carry handling during addition. In Negabinary, the carry doesn't behave like it does in binary. For instance, when you add 1 and 1, the result is 0 with a carry of -1 rather than 10. This is because the carry impacts not just the immediate next position but also the one after that, due to the alternating sign of powers of -2. Understanding these nuances is essential to avoid such pitfalls. Now let's look at two more frequent mistakes. One is failing to normalize the result after performing Negabinary addition. A valid Negabinary number must have digits that are either 0 or 1, so if this constraint isn't enforced, the result might not even represent a proper Negabinary value. For instance, an intermediate result like 201 would need normalization to conform to the rules of the system. Another common issue is implementing solutions inefficiently. This often happens when nested loops or repeated conversions between formats are used. While these approaches might work for smaller inputs, they can drastically increase time complexity and make the solution unscalable for larger numbers. Optimizing your implementation to handle Negabinary operations directly, without unnecessary overhead, is critical for both correctness and performance. When it comes to interviews, understanding the unique aspects of Negabinary arithmetic can give you an edge. This topic is less about memorization and more about demonstrating your ability to adapt standard algorithms, such as addition, to fit new constraints. A key pattern to focus on is carry propagation and normalization, as these are central to most Negabinary problems. Efficiently handling these systematically will help you avoid common errors. It's also worth prioritizing direct computation in the Negabinary format itself rather than converting back and forth to decimal, as this minimizes potential performance bottlenecks. Additionally, be prepared for edge cases, such as when both input arrays consist of a single 0, or when the result requires propagating multiple carries throughout the entire number. These scenarios often test your ability to anticipate and handle edge cases robustly. Lastly, exploring related problems like adding binary numbers or working with array-based integers can help build a strong foundation for tackling Negabinary challenges. Let's explore some alternative approaches to solving Negabinary addition problems. The brute force method involves converting the Negabinary arrays into their decimal equivalents, performing base 10 addition, and then converting the result back to Negabinary. While this approach is simple and intuitive, it's highly inefficient for large numbers due to the repeated conversions, which can become computationally expensive. Another approach is direct Negabinary addition, which processes the arrays from the least significant digit to the most significant, handling carries in place. This method is more efficient and avoids potential precision issues, but it requires careful attention to carry propagation and result normalization. A third option is using recursion to simulate the addition process. Here, you propagate carries as part of the recursive state. This approach can feel elegant and intuitive, particularly for smaller inputs, but the overhead of recursive function calls might make it less practical for larger datasets. Finally, you could use stacks to simulate the addition process. By pushing and popping digits, you can gain a clearer understanding of how carries propagate in Negabinary addition. However, this method increases space complexity, which might be a trade-off to consider depending on the problem constraints. Great job! You've now learned how to add two Negabinary numbers efficiently. We covered the unique properties of this number system and explored an optimal approach to solve the problem. Keep practicing and exploring new problems to strengthen your coding skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!